Everyone, let's talk about magnetic fields. So in the previous lecture, we derived the electric field profile as a superposition of this infinite sum, you could say, of all of these little waveguide modes. Okay, and these particular coefficients are kind of arbitrary. They will depend on how the waveguide is excited, but all of these little functions here are solutions to the electric field profile in the waveguide. And so any linear combination of them is also a solution, provided that they satisfy these little expressions over here. So given the electric field, I now want to calculate the magnetic field. So that's pretty straightforward. You just look at Faraday's law of electromagnetic induction, like so. So if I know what the electric field, I just have to calculate its curl, and I essentially have the magnetic field. Now, bear in mind, there's kind of a tradition in electromagnetic field theory, in electrical engineering specifically, to focus more on the H field, to focus on the H field rather than the B field. So we're going to say B is equal to mu naught H, because we're assuming the waveguide doesn't have any magnetic materials in it. So what I'm going to get is a negative J omega mu naught H. So for non-magnetic materials or a free space waveguide, these expressions are just kind of linear relationships to each other. And it doesn't really matter whether or not you pick B or H. It's just kind of tradition to focus on the H rather than the B. And so that's what we're going to do here. So what you get is H is equal to negative 1 over J omega mu naught times the curl of E. And of course, we don't really like this negative 1 over J, so I'm going to write that as a positive J over omega mu naught times the curl of E, like so. So all I have to do is calculate the curl of this thing up here, and I will essentially have a solution to my H field down here. So the curl is a big kind of nasty operation, but we only have the one component here of my electric field vector. So that means the curl is actually relatively straightforward. So when you plug in the definition of the curl and you assume that the y and z bits of this field are 0, what you will get is the following. That is the partial derivative of E with respect to z along the y direction minus the partial of E with respect to y along the z direction. And in this particular case, it'll help to emphasize that we're looking at just the x component of my electric field up here. So all I have to do is calculate these partial derivatives and we'll basically be done. So the partial of E with respect to y, you just apply the partial derivative operation here, and because it's separable, this sign here is going to turn into a gamma n cosine. So what we'll have is the summation from n equals 1 to infinity, a sub n gamma sub n cosine of gamma sub n y times e to the minus j beta sub n z. Likewise, we'll do the same thing over here on the z derivative. So partial e with respect to z. And again, the partial derivative is just going to act on this term here, and everything else is just going to go ahead and carry on over. So I will get the following: negative j beta sub n a sub n sine of gamma sub n y, so that's a gamma, and e to the minus j beta sub n z. Okay, so that partial derivative just acts on every term in the series, and this j beta sub n is going to come out in the front of each one. So that's it. I just plug these two guys into essentially to this expression here, and then plug it back into here. So we'll do a little bit of algebra here. H is going to be the following. I'm going to get a j over omega mu naught, and I'm going to get a summation here from n equals 1 to infinity. So we're going to pull out a couple of little common factors here. There's going to be an a sub n e to the minus j beta sub n z. So the derivative with respect to z is going to be along the y hat direction. So I'm going to get y hat times negative j beta sub n sine of gamma sub n y So you notice I factored out some terms and left the others here. And then I'm going to get the y derivative over here, which will then be negative z hat times gamma sub n cosine of gamma sub n y. And you see we factored out the common terms over here. Okay, and so we can expand this out a little bit, and that's okay. For example, this j here can distribute, so I can then say I'm going to have a j here, I'm going to put a 1, and then the j times j will be a negative 1, and that'll just kind of cancel out there. So I just distributed the j there, so I kind of squished it in here, and it killed off the other j, and that's my final expression for my auxiliary magnetic field profile. Or in this context, we're just going to call it the magnetic field. So you notice it has a y component and a z component. So it actually has a component that is longitudinal. That is, there'll be a bit of your magnetic field pointing along the direction of propagation for this wave. So that's why the electric field is transverse, but the magnetic field is not transverse. So it is TE, but it is not TEM. So put a little X there, okay? So TE, yes, not TM, and not TEM. Okay, and there is our magnetic field profile. All right, so given my electric field, this is now necessarily what has to follow out in accordance with Faraday's law.